Right, good evening, ladies and gentlemen. Good evening. Thank you. And it's my pleasure to welcome you here to SAMS, particularly our guests. And it's lovely to see so many students here too, for a very special evening, which we'll hear about in a moment. My simple task is to tell you that there shouldn't be any fire alarms. So if any go off, then we leave the building and you can follow us on the front row. Also to tell you, if for those guests here, the toilets are around the corner that way, halfway down the corridor on that side there. But principally my task is to introduce Crichton Lang, Professor Crichton Lang, who is the Deputy Principal of the University of the Highlands and Islands, and he is here in that capacity as essentially the lead and master of ceremonies of this professorial lecture. So, Crichton.
Thank you. Thank you very much. Can I just check before we start, people out on VC, can you see and hear us? If you can, just give me a thumbs up. Great, thank you. And I think the other thing to note, both just for the audience here and out on VC, is that the VC is being recorded. So just make sure everybody is comfortable with that as well. Good evening from me as well. And I'm also delighted to see such a full lecture theatre for the lecture tonight. That's really great. See, not just that there's so many people interested in coming and celebrating the awarded professorial title for Sheila with her, but also to, as I'm sure a lot of you do all the time, learn from her and for her to share some of her expertise and knowledge with us. I'm going to tell you some things about Sheila you probably already know, but I'm going to still tell you them again anyway, just in case. Sheila's a leading UK expert in the area of ecosystem modelling, using in particular the modelling tools EcoPath with EcoSim and ecological network and network analysis. And Sheila's developed EcoPath to drive forward the use of ecosystem models for marine management. Consequently, through that application of it, to really increase the impact in terms of societal change and benefit through that research. She's currently the head of the science department here at SAMS UHI, and a leader for our marine environmental science and engineering cluster. We'll say a little bit more about the research coming out of that cluster just in a second. But of course, during her time here at SAMS UHI, she's been developing in her own area of expertise in science a wide range of activities spanning both research and education. And in that context, she's held a number of leadership roles within SAMS as well, including theme leader and leading the MSc in ecosystem-based marine management. Now, throughout this time, Sheila has truly developed an international reputation. And in part, that's reflected through the number of international co-authors that appear on her publications. It's also evidenced by how often she's been asked to supervise PhD students who are studying in other countries, including in Israel, Spain, and Turkey, and to sit on key advisory groups within her scientific field. And she also runs continuing professional development courses in ecosystem-based modelling using EcoPath with EcoSim. So she's helping to upskill, if you like, and train a wide number of researchers and sharing her skills and her expertise with them. So it's education at all levels that she's been engaged with. Sheila's published over 90 papers and reports in a wide range of journals, including Ecological Modelling +1, Marine Ecology, Progress Series and Progress in Oceanography. And that publication record is in itself impressive, that volume of papers. and reports. But what is more impressive coming out of that is the extent to which Sheila's work is cited by other authors. And she has in the order of 2,200 citations in other publications. So her work's being referenced within those. And she has what's called an H factor of, I think, Sheila, 27? Yeah.
On Google Scholar.
Okay. Explain just briefly what that is. The H factor is a measure, don't ask me to explain how it works because I can't, which seeks to measure both the productivity and the impact of researchers. So not just the number of papers that they're publishing and the standard of those papers, but also the impact in terms of how often those papers are being used and referenced by others in their work. And a score of 20 is considered to be indicative of somebody who is a successful scholar. So, it's clear that Sheila has already greatly exceeded that, and in fact a score of 27 is exceeding the score that we would expect for somebody attaining professorial standing within their discipline. But the thing that I want to mention, and Sheila, I hope you won't take this the wrong way, is that that's even more of a very positive thing to have achieved in your particular discipline, because compared to some of the other areas that at the moment are very current, like clinical studies and physics and molecular genetics, the research community is relatively small. I'm not saying it's small, I'm saying it's relatively small. So to achieve that level of citation and impact within a relatively small research community is all the more impressive. Now, Sheila's publications, her what we call 3-star and 4-star ones, the ones that are viewed as internationally excellent or world leading, were submitted to the last Research Excellence Framework in 2014. And were a very key part of the submission in Unit Assessment 7, so Earth Systems and Environmental Sciences. And 80% of our submission within that unit of assessment was viewed as being 3-star and 4-star, so internationally excellent or world leading. And Sheila was very much part of us achieving that level of performance in the ref. And in fact, the impact score in that area was 100% in internationally excellent or world leading. Key thing, I suppose, turning it around, is that it's very important that the research is of that quality, because it leads to more money coming in through the ref to support research across the institution, across that research cluster. And Sheila helped contribute to that, and overall generating 1.2 million of research income through that particular government-funded stream back to the partnership. And we're going to hear more in a minute about some of those areas of expertise and specialism that really underpinned all of this achievement for Sheila. Now, the title of Professor, which we're celebrating today, represents the highest level of academic achievement which can be granted by any UK university. And it's reserved, it's not easily attained, it's reserved for individuals who are recognised as a leader in their field and have demonstrated that excellence throughout their work. Not just research, but also contribution to teaching and representation of the institution, of their academic area, of their unit, department, school, college, whatever in the UHI context. And this isn't the end of a journey, it's a mark of a point in time, and professors are expected to go on and continue to build that excellence and that impact, and really to become what Sheila already is, increasingly someone of significance within the wider academic community. And in occupying that space, to be a role model, not just within SAMS or within the UHI partnership more widely, but a role model for academics and students more broadly across the higher education sector. In tonight's lecture, Sheila's going to, as I say, share some of that expertise and that excellence with us. And specifically, she's going to explore the technique of ecosystem modelling a method traditionally used to describe the flows and pools in marine systems. And please correct me if I've got this wrong, you better do it now, Sheila. Using examples from around the globe, she's going to demonstrate how modelling can also provide insights into the effects activities such as overfishing and pollution can have on the marine environment, so that's societal impact more widely. So now, I've said more than enough. Sheila, your turn. I'm going to hand over to you now for your inaugural lecture.
Thank you. Can I ask you all to stand up, please? Stand up, stand up, stand up, stand up. Turn around. And sit down again. Really? Yes. Because I want you fresh. Come on. And then I'm also going to ask that the students sitting over there, my students and postdocs, can you stand up, please? So a lot of what I'm going to be talking about is some of their work, and I'll point them out. But I want you to know that it's not all my work. It's some of their work and a whole bunch of others. Thank you. All right, so why do I model? Why does anybody model? But I don't know why other people do. There's some modelers in the audience. You can ask them afterwards. But why do I model? And I'm going to explain why I've done the work I've done through giving you a whirlwind tour of my career. I'm going to start off by talking about the work that I did when I was a student with Tanya, who's going to stand up now. She was my
I hate her right now.
I had to do. She was my roommate at university. So I'm going to tell you about the work that I did when I was a student in Port Elizabeth in South Africa, and some of the work that I did as a PhD student on the Namibian northern Benguela ecosystem. And then from there, I moved to the States because, Africa was just too small for me. And so I moved to the University of Maryland, and I worked on the Chesapeake, the Everglades. And from there, I moved to Vancouver, where Ben was. Where Ben was at the time. And while I was in Vancouver, I actually did quite a lot of modeling. It was a bit of a sweatshop thing going on there. So there was quite a bit of models that I did in different parts of the world. You'll be happy to know I'm not going to tell you all of it about all of them. And from there, I came to Scotland, and I'm not going to let you stand up all again because you're all here now. And since I've been in Scotland, the first thing I did, Mike, where are you? Burrows, stand up, please. I worked with Mike Burrows on a model of the deep sea, and John. John Gage as John Gordon as well. And then subsequent to that, I've worked with, and these dots are in different colors because mostly in this case, I wasn't actually doing all the work. These people in the sweatshop, in my sweatshop, was actually doing most of the work. I've done some work in all sorts of other ecosystems. So you'll be lucky to know that I'm not going to talk about all of them, but I'm going to give you an example of the work that I did for my master's in the Crom Estuary. Then I'm going to tell you a little bit of the work that we did in the Everglades, mainly because those are very different from the marine systems that we work on here. Then I'm going to tell you a little bit about the decline of Steller sea lions in the Gulf of Alaska. And then I'm going to go back to my PhD in the Benguela, and last but not least, talk about the work that we're doing here while in Scotland. So it's kind of a whirlwind tour of the work that I've done. So first of all, why do we model, and where does ecosystem models fit in? Now, most of the scientists in the room really love being on this side of this graph. All we want to do is go out and measure stuff. We want to go out on the beach and count barnacles, or go and that's the stuff we love to do. The problem is the questions that society asks is on this side. And we like doing this because it's very robust and transparent and repeatable and efficient. But the problem, but society wants these questions answered. And so in order to get from there to there, we need to turn that data that we love collecting into some sort of information. And ecosystem models is a way to do that. There's other ways, but ecosystem models is one way to do that. And once you have an ecosystem model, it still doesn't actually answer the question. You need to turn that ecosystem model into some sort of evidence, some sort of indicator, something that explains that if you do this, this is going to happen. And only then can you answer questions on the Common Fisheries Policy or the Marine Strategy Framework Directive or so on. So the reason why I model is because I love doing that, but society wants me to answer those. So, and the types of models I use are food web models. So basically, stop there. Basically, what I've said to people is I'm basically like a bookkeeper for the ecosystem. So what we're trying to do is to figure out for each species in the ecosystem how much there is, how much is being eaten from one to the other, and how much of what they produce is actually turned into respiration or turned into poop, ingestion, that kind of thing. And then you try to put it all together in one big spreadsheet and figure out how things change over time. So basically, food web models is basically what they look like in general. So once you've tried to figure out how things look, how an ecosystem look in one time, this is another way of looking at that, you can actually look at, it's called mass balance, you can actually look at how that changes over time if you influence it. If you make a change, how does that affect everything else going on in the ecosystem? And once you've figured out how that works, you can figure out how things change in space. So the ecopath with ecosystem with ecospace software suite is what's described here. And most of what I'm going to explain to you in the beginning of the talk is up here, and then I'm going to talk a little bit about stuff in there, but I'm never going to get to there because that's the stuff that Natalie is doing, actually. Okay, so that's basically the software technique I use. So let's go to the examples. The first one I'm going to talk about is the work I did for my master's a really long time ago. And for my master's, I worked on this estuary called the Krom Estuary in South Africa. And the Krom Estuary is a very beautiful estuary, and it has a very expensive marina there. And the problem is that the water flow through here got really polluted, and there wasn't a good water flow, and so obviously people were worried about what's going on in the estuary. So we were asked to look at what does the ecosystem look like, and to do that, so the Krom Estuary is a long estuary. The marina is down here, but we basically sampled these little critters, which are Apogibia and Callianassa. They kind of fresh, they sand or mud prawns. So I went and sampled these. This was probably the last time I did actual field work for my own work. Sampled these, counted them, and then incorporated them with all the other data from that ecosystem into a food web model. And that's what it looks like. So these were actually hand created, and they took a very long time. But actually, to get the values took a very long time as well. So that's what I did for my master's. But why was it important? It was important because prior to 1984, in 1984 they built a dam in the top of the river, and basically the flows of water changed in the ecosystem. So over time, the ecosystem changed, and it changed whereby there was no freshwater inflow coming into the system anymore. And so the salinity in the water changed from a sort of saline, estuarine system to a more marine system. The temperature changed a little bit, but also some of the other descriptors of the ecosystem over time had changed. And when you look at, how the system changes as a whole, the emergent properties of the system, we saw that there were differences in a whole bunch of indicators which you don't really need to worry about. But what we found out was that the estuary had changed from a system that was dominated by plankton, so those are the little plants that float in the water, to a system that's dominated by more submerged vegetation and microbenthic activities. And this was because of the freshwater inflow. So the ecosystem had changed, and that has actually been caused by the changes in the freshwater inflow. So that was my master's. Then I'm going to talk about another system that's not quite marine, and I'm going to talk about the South Florida wetland ecosystems. So this is when I went to the University of Maryland, and we worked on this ecosystem. Actually, I'll go back here. I worked with Bob Ulanowicz, who is a really lovely man. And he had a postdoc named Cristina Bonavelli, and she started this project, and I finished it because she had to go back to Italy because she I think it was too cold for her in Maryland. Natalia will understand that. And so in this project, basically what we were trying to do is to compare the 4 different ecosystems. So in the Everglades, you have a lot of fresh water flowing from this area into Florida Bay. And so obviously you have much less salinity up here in the graminoid marshes. The swamps have a bit more salinity. The mangroves, again, more saline. And then Florida Bay, they're 4 very different ecosystems. And so what we were doing is trying to basically look at these 4 ecosystems and explain why they're different. So in the beginning of my career, a lot of the questions I was asking was, what does it look like and why does it look that way? And it's a much more blue skies question. It's not as applied. You're just trying to figure out how things work, essentially. So these 4 ecosystems had very different vegetation, and I'm just showing you some of it. In the graminoid, in the marshes, you have obviously sawgrass, so these are just grasses. A lot of periphyton. Periphyton, for those of you who aren't scientists around here, it's like crusting stuff that grows on things, essentially. I'm trying to make it less scientific. And then it had a lot of floating vegetation. But this ecosystem was very two-dimensional. You can see that there's not big trees. Then in the next ecosystem was the cypress marshes, and you can see cypress swamp, and you can see there were lots of swamp trees, lots of very different vegetation in that system. And when you have very different vegetation, you also have very different species living on it, and so the ecosystem is more complex. The mangroves, obviously, lots of mangrove trees with different types of mangrove trees, but also other vegetation in there. And then, obviously, in Florida Bay, you had seagrasses, which is a very different system, and lots of drifting phytoplankton, drifting algae and phytoplankton. So these 4 ecosystems at the bottom of the ecosystem was very different, and therefore, over when you describe the whole of the ecosystem, they're also very different. And the one thing that we found when you use a network analysis, which is what we used here, is you can figure out how dependent the whole ecosystem is on that one bottom of the food chain. And we found that the graminoid marshes was significantly more dependent on this periphyte and this sort of crusty stuff that doesn't really look very good compared to some of the other systems. And we also found that there's a lot more recycling in some systems than there are in others. And that is very much related to the salinity gradient. So there's a lot more in there, but just to conclude there from that study, then we found that the graminoid marshes were quite an efficient system. They're very good at moving energy from the bottom of the food chain to the top, but it's a much more fragile system. Whereas the cypress swamps were more stable, and the mangroves of the 4 systems were the most resilient. So if you actually perturbed the system, the mangroves would would recover quicker. And we found that the salinity gradient was seen in many of the indices that we looked at, which you were glad to know I didn't tell you about, but that the mangroves were definitely the most resilient. So that's the second part. So then from there, from Alaska, I went to the Fisheries Center. And I worked there on a few different projects, but the one I'm going to talk to you about is basically the Gulf of Alaska project, where we looked at, and this is work that I did with Sylvie Gannett, she was another postdoc, and the PIs that we were working for at the time. And the project was all about the decline of Steller sea lions. So the big problem in this system, and actually a lot of us were funded, including Ben, I suspect, to work on the decline of Steller sea lions in the Gulf of Alaska. The big problem in this ecosystem, and so this is a Steller sea lion, the problem is that from the 50s onwards, the Steller sea lions on the western side of the Gulf of Alaska, the Aleutian Islands, had increased to about the mid-70s, and then there was a precipitous decline. So all of a sudden, they were all dying off, and nobody knew why. Whereas on the eastern side of the Gulf of Alaska, so in the Alaska part of the Gulf of Alaska, not the Russia part, the Steller sea lions were increasing. And they weren't at the same level, so there were loads more in the Aleutian Islands than Southeast Alaska, but they were not showing the same decline. And in fact, this is a large ecosystem that is very connected. So the question is, why is it doing one thing on the one hand and something else on the other? So that was the question we were trying to answer. And we did that by building 2 ecosystem models for these 2 ecosystems. So for Southeast Alaska and the Aleutian Islands, and when you build these types of models, it's really important that you build them to look the same, that you actually make sure that you don't put something in there that's an artifact of the way you think the world works. So you want to make sure that they kind of look the same. So we did that. And we also used over time, so we did the same thing as I've talked about in the Crom Estuary and in the Everglades, where you're basically just trying to figure out how the thing looks in one time step. And we kind of did that first. And then we basically looked at how has it changed over time. So you do that by getting some data, and this is data that we have for the ecosystem, for the Aleutians, so for the western part. And you can see that we don't always have data going back far enough, which is always a problem in modeling. But the other thing you see is that the biomass, so the amount of fish there's in the water, is kind of, there's no real trend overall, but the catch over time in the Aleutian Islands has increased overall. And on the other hand, in Southeast Alaska, the biomass seems to have increased over time, and the catch for most species, except for salmon, has declined kind of over that same time period. So you can see that it's not just the Steller sea lions, but it's actually also the fish species. So again, we were trying to figure out why is that. And so there's obviously a whole bunch of different things that's changing in this ecosystem. The catches have an impact. So if you take fish out of the system, it obviously has an impact. But the other thing that has an impact is the environment. And so there were a few indicators of how the environment has changed over time, and there's a whole bunch here. The Pacific Decadal Oscillation, the Arctic Ocean Index. Oscillation Index, thank you. The Aleutian Low Pressure and the Regime Index. There's a whole bunch of different ones, and there's loads of papers published over them. So we looked at all of these, and we kind of tried to use the ones that worked the best for us. And the one that worked the best for us was the Pacific Decadal Oscillation. It's the one that actually gave us better fits for our model to the data. And the Pacific Decadal Oscillation is a very esoteric index, which basically is an index of sea surface temperature and sea level pressure. And what we found is that this index is very different when you're in the in Southeast Alaska or the Aleutian Islands. So you can see that there's a red-blue split there. And the red-blue split there means that it's doing one thing on the one side of the Gulf of Alaska and something else on the other side. And when we figured that out, it actually made a lot more sense to what was going on in this ecosystem. So what we had to do when we were driving our model forward was to actually flip this index for the Southeast Alaska and use the inverse. So use the inverse for the one side of what we use for the other. And then we got the model to fit our data better. So to do that, the best fit of our model here, so this is just biomass, so just the amount of fish in the water. You can see the data here is the dots, and the lines is the blue line is what the model predicts. And when we use that driver plus fishing in our model, this is the fits we got. And if we don't have that driver in the model, then that's the fit we got. So you see that actually the line isn't falling on the dots as much in the red line. That's the important thing for those of you who aren't scientists out there. So in the Aleutian Islands, that's what we got. And in Southeast Alaska, that's what we got. So again, we got better fits by and large for when we put the environmental driver in. But obviously, the reason we were actually there, and the reason they were paying us 2 postdocs for 3 years is a lot of money, was actually to figure out why the Steller sea lions declined. And so we had to answer the question. So what we did here was basically, so what you're seeing here is the abundance of Steller sea lions over time. The dots is what the data is telling us, and the line is what our best fit model is. And the nice thing about models, and actually, for me, the most useful thing about models is that you can play God. You can actually say, okay, this is what we know happened, but what if something else happened? And there are a whole bunch of hypotheses about what has happened. The first one is that, over time, we've fished out all of the species that Steller sea lion eat, and therefore, if you don't have food for them, then they will collapse. The second one was that killer whales have actually been eating the juveniles of Steller sea lions, and so the killer whales have actually decimated the population. The third one was that actually they're competing for their food with other species, so arrowtooth flounder is the specific species that they really compete with. And then the last one is that this environmental driver, the ocean drivers, have actually caused the changes. So because this is a model and you can play God, we decided, okay, what if in the first instance, and the main decline happened after sort of the mid-1970s. So what if in 1977, I think it was, we basically fish out all the arrowtooth flounder? In the model, you put in a huge fleet, you just go in your model and you say, okay, let's chuck out the arrowtooth flounder. And if you did that, you see that the model actually still predicts that you would get an increase and a decline. So the decline happens as it was, pretty much. But you don't get as much of a decline at the end. So over time, you only see the difference at the end of the simulation. So obviously, arrowtooth flounder isn't a bad guy here. So the next thing we looked at is, maybe it's the fisherman. Maybe the fisherman has fished out all of the food that the Steller sea lions are eating, and so let's stop the fishery. Let's just say, okay, in 1977, you stop fishing. So if we do that in the model, then that's what we get. So still, you have an increase and a decline till about the early 1990s, and then you get a bit of a recovery. So the Steller sea lions don't decline as much in this iteration, but you still don't actually get the model. But you still don't get, the Steller sea lions don't just keep on living in the model. So that's not good. Then we said, okay, what if it is the killer whales? What if really the killer whales are actually catching all of the Steller sea lions? And to do that, again, you could do this in a model, but you certainly couldn't do this in real life. We went in and shot all the killer whales in 1977. Again, you can, actually, maybe you could do that in America, but and definitely in the 70s, but maybe not. So if you did that, you can see that, okay, you still get the increase and the decline, and from about 1990, you would actually get a flat line. So the population would not have declined as much if you didn't have killer whales at the time. However, you had to stop them. You had to stop all killer whales in 1977 for it to get an impact in the early 1990s. So that was really interesting. And then finally, if we didn't have this environmental driver, if actually you didn't have any climate changes, not a climate change thing, but if you didn't have any changes in the environment, if the specific decadal oscillation didn't happen, then that's what would have happened. So if you didn't have a Pacific decadal oscillation in this model, i.e. this ecosystem, you wouldn't have gotten the increase in the number of Steller sea lions, but you also wouldn't have had the decline over time. So what we can say from that is actually, in fact, the environment has caused, has caused some of the increase that we saw, but not, it hasn't really had that much of an impact on the decline. Or I should say, it didn't cause the increase, and therefore it didn't cause the decline. But if you had to have any of the or none of these other options, then you would have actually gotten a stable population after about 1990 with the environment. So again, fishing and climate was an impact here, and it's for all different species, which I hadn't gone into in any detail. But really, the take-home message is that the Steller sea lion decline is explained by all of the factors combined. It's not just one of those things. So there's not just one person in the whodunit that did it. They all did it together, essentially. Okay, so that was the first chunk of the talk. So next I'm going to go back to my PhD because it made more sense in the way I'm telling the story here. And for my PhD, I started off similar to what I did in the Crom estuary, trying to figure out how the ecosystem works. And this is the northern Benguela ecosystem. This is kind of what it looks like. You have a big desert, and the water, the sea is right there. So there's not a lot of vegetation there. And so the ecosystem that I modeled in this case was basically from the coastline, from what you see in the background, all the way to the 500-meter depth contour, and it's all along the coast of Namibia. And that ecosystem is really interesting because it's a huge upwelling system. So lots and lots of nutrients coming from the bottom, and it's a very productive system with lots and lots of fisheries. And it has a very large upwelling cell off Lüderitz, which is kind of at the bottom of the northern Benguela, so which is around the area where South Africa and Namibia splits, essentially. And that causes this ecosystem to kind of split in two. So it's actually, for some species, they can move backwards and forwards across that boundary, but for others, it cannot. So it makes it for a really interesting system. And it has huge amount of upwelling. There's a huge amount of nutrients in that system. Again, I spent the first part of my life doing that, creating these crazy food webs, which really only looks pretty and actually gives you tendonitis in your shoulder to do. But it doesn't really tell you very much. But they did give me a PhD for that, so that's good. Not just for that, but that was a very big part of it. So the next thing I did in that, for that particular ecosystem is working with some other colleagues from South Africa. We looked at how the ecosystem had changed over time. So the ecosystem model I built was for the 1990s, but the other two people in this study had actually looked at the ecosystem in different time periods. And so the different people had built different models. And the thing about models is that they're very personal. The way I build a model is very different from the way another food web modeler will build a model, because things are important to me that aren't important to other people. So if you have 3 different people's ecosystem models, you have to standardize them. You have to try and find the common ground where you all can agree that this is important to all of us. And so what we had to do was to try and find the least, the most common denominators between all of our models that could explain the ecosystem similarly. And so this is what we did here, and it tells you where the data come from and so forth. And this is kind of what the ecosystem looked like. So it had a whole bunch of different species at the bottom of food chain, so all the plant species, phytoplankton, benthic producers, the sort of zooplankton, and lots of fish species, because that's what we were interested in, and then mammals and seabirds and so forth. And what we found in that system is that the ecosystem, in that study, is that the ecosystem had changed quite a lot. So the catches in the ecosystem, so the stuff that people really care about, really, had changed quite significantly. So from the 70s to the 80s, it stayed relatively stable, the overall catches, but the distribution of catches changed. So you have, in the beginning, in the 1970s, you have quite a lot of sardine, but by the 1980s, you have a lot more horse mackerel being caught. And then from the 80s to the 90s, you have a huge decline in the catches. And you can kind of see it in the total catches at the top there. And we also found that over time, the biomasses in the different species had changed. So we saw that a lot of species had increased in biomass. A few species declined from the 70s to the 80s. But from the 80s to the 90s, most of them had declined. So really, and these are the important fish species. So there's definitely been a huge change in this ecosystem. And we found that the 1980s system was still resilient, but by the 1990s, the system was stressed. And you do that by looking at the emergent properties of this ecosystem. But what we had done in this case was to look at snapshots of the ecosystem over time. So you look at the 1970s, and you compare them to the 1980s, and then you compare them to the 1990s, but you don't actually look at how things have changed over time. So there's no dynamics in the system. So the next study that I'll tell you about is basically where we looked at how the system had changed, and we looked specifically at the regime shifts that might have happened. So a regime shift, the definition is here, but what it basically means is if an ecosystem is kind of here, it's kind of happy where it is, but you push it a little bit too far, then it might fall into a different area where it can also be very stable, but it's not really where you want it to be. So an ecosystem is quite adaptable up to a point, and if you push it past that point, then it goes into a different state, and then it's really hard to get from there back to there. So that's kind of what a regime shift is, and this is kind of what we were trying to show here. So in the Northern Benguela, I showed you those snapshots of catches, but this is what really happened over time. So from 1956 to 2003, I think we have the data here, You can see that the ecosystem, you had quite a lot of sardine catches going over to horse mackerel catches, and your hake catches has also declined. And over time, you had lots of anchovy, but that's also declined over time. So by and large, the catches there's been a precipitous decline in catches. At the same time, that ecosystem has increased, the temperature of the ecosystem has increased. Now, this is an upwelling system, so it's based on nutrients coming from, with the cold water coming from the bottom. So, and the ecosystem is therefore created to depend on that nutrients from the cold water. So this increase in sea surface temperature would have a huge impact on the system. So when over time you have large decline in catches, big increase in temperature. So things have happened in the system. So now we have an ecosystem model that has 32 functional groups and lots of fisheries. So we're trying to explain how the system looks over time, and we kind of then go and see how it changes over time. And again, this is the same thing. You have the dots is what the data is telling you, the lines is what the model is predicting. I'm not going to go into detail other than to say we've kind of looked at the dynamics and tried to reproduce the dynamics of the ecosystem. So the next thing we did then was to test the hypothesis that this ecosystem had reorganized. It's basically changed from one thing to another over the last 50 years, and it was basically because of overfishing and the drivers, the change in sea surface temperature. So we created a model for 1950, we fitted it to time series, and we did a whole bunch of statistics for those of you who are interested, which I'm not going to go into any detail, but I can talk to anybody who's interested afterwards. So we used a statistical technique called STARS, which is a sequential t-test analysis for regime shifts. And what it does is, so this is basically the temperature driver. So when temperature goes up, the nutrients goes down. So again, we flipped it in this case. So we did this analysis to basically look at where the ecosystem has broken. Where's the regime shift happened? In this case, specifically in the inverse of your temperature, your driver of the ecosystem. The other thing that's worth noticing is that there's these only three that's very noticeable, large increases in temperature or decreases in this index, which are called Benguela Niños. They're kind of like the El Nino, which I'm hoping most of you have heard of. And what happens actually at that time is that the wind stops blowing, essentially. And when the wind stops blowing, you stop having nutrients coming, you stop having upwelling, you stop having nutrients, and it has a huge impact on the ecosystem. And the wind stops blowing not just for a day, which would be nice here, but, for like months. And so that's basically what they call Benguela Niños. And they're actually usually sort of a year or two after normal El Niños, but not after every El Nino, actually. So we used this STARS analysis here, but we also did it on the landing. So you can see that there was a break, a regime shift in the landings in sort of the early 1960s, and then one in the early 1980s again. So we're using this statistical analysis to just show you where the trends are changing. Then it's called a traffic light plot. So all I'm showing you here is just all of the drivers in the ecosystem. So all of the catches, all of the sort of fishing fleets, and sea surface temperature. And it's just a traffic light plot, so anything that's red basically is high, and anything that's green is low. So you can see, if you just look at it, and you won't be able to read any of it, but you can see that some species were high in the beginning, and other species are high at the end, essentially. And so it's just a really good way of looking at lots of data over time to see if it's changed from high to low, essentially. But then you can also do this where you can see how the ecosystem has changed over time using a principal component analysis. And what we found is that the system had changed from the 1950s on this axis, from the 1950s to early 1970s here. And then it changed on this axis from the 70s to the 80s, and then it changed again. So it kind of just gives you an overview of how the system has changed. And those two axes happen to be very much related to the hake fisheries. Hake's a bit like cod. They kind of live more, not here, but in the northern Benguela, they live more on the on the bottom. So this is basically due to the hake fisheries, and this is basically due to the sardine fisheries. Sardines are pelagic fish. They live in the midwater. So they live in very different parts of the ecosystem, and the impact that the fisheries has had, the hake fisheries there, but here not just the sardine fisheries, but also the temperature has an impact there. And this is another way of looking at it. I think I won't go into too much detail, but you can kind of see how things have changed, and they're different for the different parts of the ecosystem. And then once we've run the model with all of the drivers that we have, and we kind of get the predictions of the model, this is what we're seeing here. So you can really see that the model has predicted very big differences. So in this case, sardine, tuna, and anchovies are very high in the beginning and super low in the end. Whereas, for me, it's hard to read. Seals are kind of really low in the beginning, high in the middle, and sort of going down at the end. But things at the top here are the things like gobies and jellyfish, which are also pelagic groups, but they're not the ones that we want to fish. And they were very low in the beginning, and they turned out to be very high at the end. And so that actually shows you that this system has changed from something that looked like that to something that looked like that, essentially. And this is just a depiction of explaining specifically what's happened in that pelagic section. So this is, if you look at, on average, what the pelagic ecosystem looked like up until the mid-1970s, you can see that, and actually if you look at the bottom here, everything that goes from the environment to phytoplankton is basically how much energy is being produced by the ecosystem. You can see that that's not very different over time. There's not really a big difference on average over those 3 years. But the way the energy is being distributed between the two different parts of the ecosystem, the bit that we like to fish, anchovy and sardine, and the bit that we don't like to fish, gobies and jellyfish, have changed. So before the 1970s, the energy distribution between sardine and anchovy and gobies and jellyfish was quite equal. See, there's very similar amount of energy flowing to the two parts. And the interesting thing with anchovy and sardine and gobies and jellyfish is they eat each other. They'll eat anything. And if you happen to live at the same place, they'll eat each other's young. And so you see that there's a lot of energy flowing from the gobies and jellyfish to the anchovy and sardine. So they're eating each other, but the main flow is going to the anchovies and sardine. So anchovy and sardine in this time period was really important to this ecosystem, and it was very highly fished. So lots of fishing happening. Then after the early 1970s, the ecosystem had completely changed. And all of a sudden, you still have the same amount of energy going into it, but all of a sudden, very little energy is going to sardine and anchovy, and way more to the gobies and jellyfish. So the ecosystem has obviously rearranged itself. Sardine and anchovy, not so important. They're still being fished like hell. They're still being completely overfished. Well, they're being overfished because we didn't realize. And there's still energy flowing from the gobies and jellyfish to the sardine and anchovy, because they're much better at eating the juveniles of the others. And they're still being fished really highly. And then after the mid-1980s, you have a much worse system again. So again, very little energy flowing there. And at this stage, there's hardly any fishing happening because the fisheries had collapsed. So this is just a really good way of seeing over time, the ecosystem had really rearranged itself. And then the way we can look at that is to look at these emergent network analysis indices, which you'll be all happy to know. I'm not going to explain, and I'm not going to put up any formulas. But the two that are really interesting is the redundancy, which is basically how the energy is distributed in the pathways in the ecosystem, and the average mutual information, which basically shows how organized the flows are. So if you have a reorganization of the flows, which is what's happening here, which is what we saw, is that you have a reorganization in the flows in the 1970s, and then the system was kind of stable, and then you had another reorganization of the flows. And what you also see is that the system had lost, if you don't look at the straight line, but you just look at the kind of general trend, the system had actually lost redundancy over time until there was a big break in 1984, which was when the big La Nina happened. and then the system had lost complete redundancy. So essentially, the point is that over time, the fishing had really changed the structure of the ecosystem. And, during the 1963 El Nino, Benguela Nino, and the 1972 or 3 Benguela Nino, the ecosystem could handle it because it still had a lot of distribution and flows. But the moment you start, you basically reorganize the system, and then you hit it with not a very strong Benguela Nino. It doesn't even show up, really. That actually pushed it over the edge. And so that's kind of the bottom line here. So the combination of fishing and sea surface temperature had reorganized the system, and you have this large reduction in redundancy after the 1984 Benguela Nino, which changes the system abruptly. And the important thing is that the system should now be managed in a very different way. You cannot imagine that you're going to have the big sardine fisheries that you used to have, because the system is not the same anymore. And nobody wants to eat jellyfish, unfortunately. So that's kind of the nearly the last bit. The last thing I'm going to talk about is some of the work that we're doing at the moment here at SAMS. This is work with Mike and Natalia and Simone. And it's called the Marine Ecosystem Research Program, or MERP, which is a very catchy title. And the aim here is basically to incorporate existing data and new data, which is what Mike is doing, going out and actually getting real data, into our models to understand how the ecosystems work. And to do that, we've created yet one more of these food webs. So see, it's all the same. But what's interesting, and we've done precisely the same and a whole bunch more than what I've told you what we did in the Benguela. But what we also looked at is how temperature influences these species. So what's interesting is that in the waters out here, you have species that like it warm, like Natalie and I. She's Italian, I'm South African, we want some heat. And you have species who don't mind it cold. People who don't mind being cold. And so species like cod, for instance, they don't like heat at all. Whereas species like horse mackerel, they're happy anywhere pretty much. And even herring, they're happy anywhere. And so if you put my comfort zone for the species into the model, and you put temperature in as a driver, you can actually see how this species is uncomfortable actually has an impact on how well your model is behaving and how well the ecosystem will respond in future under climate change scenarios. So these are the climate change scenarios that comes from the IPCC, and there's different scenarios, and I'm not going to go into detail. You can ask Natalia about it. And so this is just some of the results that we've got from it. So the dots, again, are what the data is telling us. The lines is what the models predict. And I'm giving you 4 different species here. But what I've looked at, what Natalia looked at, is basically under different future scenarios, how would these species respond? And so what's interesting is the solid black line is if you just didn't do anything and there wasn't any climate change scenarios, what will happen is you'll have more grey seals, essentially, and your cod will collapse. Your saithe won't be too bad, but your whiting will collapse, pretty much. However, if you actually manage the fisheries well at what the maximum sustainable yield is called, basically what the government is telling you to manage the fisheries at, and the government is managing fisheries at, then you'll get better results for cod. Cod will actually increase. And whiting, saithe won't do so well, unfortunately. And that's all good and fine. But if you then put the environmental driver, if you put the temperature effects of these species who like to be warm and like to be cold on that, then you get a very different result. So cod, unfortunately, don't like to be warm. And so over time, the temperature goes up and down, and so you might have some cod for a little time, and then you won't have any cod after a while. And different temperature scenarios, whether the 2.6 scenario, the 8.5 scenario, that's there's a lot of wiggle room in there. But the worst case scenario means we're not going to have any cod by about 2040, 2050. But other species like whiting, who really don't mind it being hot, is actually in that scenario is going to do really well. So the bottom line is don't eat cod, eat whiting. Or saithe, actually. Although saithe isn't doing that well here either. So rising temperatures have impact on the cold-loving species, and it's really important to include these environmental drivers into the ecosystem approach to fisheries management. You have to be able to do that, because otherwise you're making decisions on what to manage, how to manage your fisheries, but you don't take all the information into account. So the next thing we're doing, and this is actually hot off the press, Natalie has sent it me this morning, so this is completely her work. And Simone, so what we're doing now is looking at how do people want to manage the ecosystems in the future. So there's different scenarios. They're called nature at work, or local stewardship, or national security, or world markets. In world markets, basically, you just want to take all the fish out of the sea and, put the money in the bank, essentially. And local stewardship is you want to protect the ecosystem. So they're really wide-ranging scenarios of how the future might look. And if you drive the model forward in different ways, you'll get different results. So you can see here we have different results for nature at work. Will give you more grey seals and more saithe, but not so many scallops. And your cod's never going to recover. I'm sorry. It's just not going to happen. Whereas national security with lots of fishing will actually give you more scallops, for instance. So just looking at possible future scenarios that we can inform policymakers with, that if you do this, this is what might happen, essentially. Not that we tell you what to do, but just that if you do this, this is what might happen. So that's the kind of the next bit of work that we're doing there. The other thing we're doing is also looking at indicators. So again, it's all good and well to wave my hands around here, but sometimes people need a number. And so looking at indicators is a way to do that, is a way to kind of get to that point where you can influence policy. And so this is just, I'm not going to go into too much detail, but we basically have two models, the West Coast, which I was talking about, but also the Celtic Sea. And these models are very different. And in fact, for the Celtic Sea, we have two models that were parameterized not by us, but by somebody else, and by two other people. And so they have two different parameterizations of that model. So what I'm showing you here is basically just indicators over time. And you can see the important thing is that the green is different from the blue, i.e. the West Coast is different from the Celtic Sea. But you can also see that two different parameterizations of the Celtic Sea, the green and the black, are also different. So it's really important that you understand what goes into these models and that you're sure that what you put in there is actually representative of what's happening in the real world. And these indicators are really useful then for management in the future. So they're useful, but it depends on the models. It really depends on the modelers, actually. And they are very much influenced by the assumptions that you make. That's really important. So you need to be confident about your models. And if I can go back, which I hate people doing, but I will anyway. I don't know if you can see the grey lines around here. The grey lines around here is basically the confidence intervals that we have, i.e. we're not confident about what's going on here, but we may be more confident what's happening there. So you really need to look at the confidence that you have in your data. And we haven't done that for the green model here, essentially. So really important. It's good to get to that point where you can have an indicator, but you have to have something you can trust. So, I've said that already. So, getting back to the Y model. So I think I've shown you that you can model at this side of the spectrum where you're just trying to figure out how it works. You just get your data, you put it in, and you try and figure out how it works. And then you can get to a place where you can figure out why it works. Why does things happen? But what I'm trying to do, at least, is get to this point where I can say, okay, we know this is what happened. We know this is what you want to happen. So let's get to that point where we can actually inform policymakers. So finally, why do I model? Well, why should anybody model? Mainly because it's much quicker than going out and getting data. But in reality, it really allows you to understand how the whole ecosystem works, not just a part of the ecosystem. And it helps to understand what the impact of human interactions are. What's the impact of a dam that you built in the upper parts of the river? Or what's the impact of fishing? What's the impact of climate? What's the impact of all of them together? The cumulative effects of them. And it helps you answer management questions or even ask management questions. but it's just a good way to play God, really. And you get to travel the world. I mean, it's perfect. So I just want to thank everybody. Thank you, UHI, for giving me a professorship, for doing what I love, which is amazing. Thank you all for coming and staying awake, most of you. And questions?
It's my job to compare the questions that I hope you all have for Sheila.
You have to stand here because they can't see you.
Of course.
Maybe we should start with the people on the VC.
Absolutely. Thank you to all who listened on VC, and hopefully you've
understood it,
and got it and everything. So if anyone's got any questions, I can see Neil on screen, but I'm sure there's others there, please fire away.
Neil? Yeah?
Can I ask a question? Sheila,
yes.
Yeah, it's an observation. I'd welcome your comments on the observation. But first of all, just a personal note, congratulations, Sheila. It's great to be able to celebrate this event with you. There's an interesting link between your inaugural lecture and my inaugural lecture a couple of weeks ago, which is, and as you know, and colleagues will know, that we're from completely different disciplines. I'm not a scientist, I'm an educationalist. But in my inaugural lecture, we were talking about the ecosystem in the sense of a classroom and the dynamic between individuals in that classroom, students, lecturers, moment by moment, and how that builds up into what is termed as an ecosystem within that very human context. I suppose my observation is that the link between what you've been saying, Sheila, and what I was saying is this notion that until and unless you have that very detailed forensic analysis of the ecosystem, whether it's a classroom or whether it's an S3 setting, some of the examples you gave, until you've done that, we're just not in a position to create policy, whether it's educational policy or whether it's scientific policy. And I think that's for me, that's quite an interesting link between what you were saying and what I was saying a couple of weeks ago. But I know you weren't able to attend when I spoke, but I'd be interested in any observations you would make about that principle of intricate exploration leading to really good policy, because I think that's the key. For me, that's the key of it, really.
Yeah, no, I totally agree. And I mean, the networks that's underlying all of the stuff I've actually not talked about here is no different than a human network. The data is the same. The unit might be different, but actually it's just information. And so, yes, I totally agree. And if you don't understand the kind of holistic depth of it, then you'll make wrong decisions, I think.
Thanks, Neil. Anyone else in VC land has a question?
No?
I have one from the floor there.
Okay.
No, the first example that you gave about the river that had been affected by the dam, did anything actually come out of that?
To be honest, I don't think so. Quite often, academia, we get really involved in our own worlds, and we think, oh well, there's impact. Let's see if we can see what it looks like. But if you don't link it up with policy, or if you don't get asked to do it by people in government, then they often don't listen to you, or they don't see what you're doing. So I guess it's really important that we communicate what we do. And in that case, I doubt it, because South Africa has huge problems with water, so they probably need the water more than the people in the very expensive marina development need their fresh water.
Anyone else?
Yeah.
I'm curious about the Namibia event, close to Namibia. And so if upwelling virtually ceases, wouldn't that affect primary productivity?
It totally does. I mean, that's why it all stops, because the upwelling ceases, so you don't have any primary production. And I mean, we even have species, really warm water species, coming from the south, completely different species that are coming from Angola. And during the 1985. No, there was another one in 1995, Benguela event. I was there, actually, and you had loads of species dying, and also you then get all the microbial loop starting to go, and then you get anoxic conditions and lobsters walking out on the beach. And I mean, it's a really horrible place when it happens. You wish for the wind, which is unsurprising. Can't imagine it, but yeah, it is really, it does affect it starts at the bottom of the food chain. That's where it starts. Yeah. Paul?
Yeah, so Sheila, I've asked you this question before, but I've forgotten the answer. It's about primary production in ecosystem. Do you have to input data for primary production, or does the model calculate what is needed to support the rest of the food chain?
It depends on how you parameterize it. You can do either. It's better to put the data in, actually, because you need to constrain the model at the bottom.
So in the case of the upwelling system, did you have primary production data?
No, in that case we didn't. No. Yeah, so it was calculated by how much primary production was needed to get the model to get the data.
Did that look realistic?
I don't know the answer to that offhand because I didn't look at that. And actually, that's the one thing. As time progresses, you get much better at actually looking at those kinds of things. And because the Benguela, I've been playing with it, but not really looking at it as we have been on the West Coast. It needs a lot more of that uncertainty testing that Natalie has done so well. So.
What I was thinking about, almost the opposite in terms of what additional constraints we can put on models to make them coincide a bit more with reality.
Yeah, we can have a chat about it.
You will know. You invited me to speak a bit more about it now.
Well, I think making sure that you have some constraint on your primary production. So making sure that you have some data. So in that ecosystem, we don't have a time series of data to constrain our primary production, for instance. Or if we do, if there is, I don't have it, I should say. So the thing that's actually constraining that ecosystem is the nutrients or the link that there is between sea surface temperature and phytoplankton in that specific ecosystem.
There's a question somewhere in the middle.
Yeah.
Do you have any examples of those ecological shifts where they've reverted back to what was before, so after the, and if not, what would be needed to drive that in the model? Theoretical sort of situation.
That's a really good question. I don't have a know of a paper that's done that, so I don't have scientific proof, if you know what I mean. But I've always thought, and I've always wanted to actually look at the changes in the Newfoundland fisheries, for instance, or even the North Sea fisheries, because it changed significantly, and then it's changed back. You're getting more cod and other species now. So I think, is that a regime shift, or is that just the ecosystem changing over time? And that, I guess, depends on your definition of regime shifts. But I don't know of any papers anywhere where it's actually been shown to have reverted to what it was before. Yeah.
Is there not the work done in the Western approaches, that very early work, Hardy's and others, where there was the shift between pilchard and sardine,
yes,
and Sagitta, elegans and Setosa? That was...
Yeah, so that there are those, but those are not regime shifts. I think those are flips. They're not really called regime shifts because the whole ecosystem doesn't change. It's just one layer of the ecosystem. There's a word for it. I've forgotten the word for it. But they substitute for each other, the two species. And I think they found similarly in the Humboldt or Peru or somewhere in that upwelling system that there's the anchovy and sardine substitute for each other, and they were kind of hoping that was going to happen when the anchovy died off in Namibia, in Benguela, that the sardine was going to, increase, but it didn't, because the problem is the thing that substituted was jellyfish and gobies. So you might think you know what's going to happen, but all of a sudden something comes out of the blue that you hadn't anticipated. Yeah.
what was happening with the salmon in Alaska?
So salmon in Alaska is a really interesting thing. So salmon in the Pacific, unlike the salmon here, the salmon in the Pacific lives for 4 years. And they go back to their rivers every 4 years to spawn, and then they die, right? So the problem with salmon is, for those 4 years, they're in the Pacific, everywhere from Tokyo to, I don't know, San Francisco, you can find salmon. So you can't model what happens with salmon with an ecosystem that's so small. You have to model it with an ecosystem that's like that. So you have to, if you want to figure out what's happening with salmon, you need to look at the whole of the Pacific to get a good handle on it. And so we had to put salmon in there because salmon is really important in Alaska. So sometimes you have political reasons for that. But also, salmon eat a lot as they go through the river, and they eaten a lot as they go through the river. But you can't reproduce the trends for salmon in that small area if everything that's happening in the wide world is impacting them. And so what we did in that case was actually to drive the model for salmon with the data. You're not actually trying to estimate what the salmon look like, but you're actually taking that data, knowing that that is what happened with salmon, and putting it in so that there's food for the things to eat, and it's eating stuff, but you're not actually trying to predict what they look like.
You talked about how with different, because models are so personal, we have to kind of keep comparing, we look at the relevant relevant things that we look at.
Mm-hmm.
But in terms of standardization of modeling techniques, has there been anything that you've heard of to do with getting a sort of type model standard set for a particular ecosystem?
The thing is, because models are quite personal, and because they are, they have their foibles. It's a little bit like one person's painting of an ecosystem of a thing and another person's painting. They'll just not look the same, right? It's not a photocopy. So I think it's not a good idea to have just one model. So the best thing to do, and the thing we're doing in MERP actually, is to have different models and try and see if you can get the same answer with different people's perceptions of what the world look like. And I think that's a much better way to go. That's what the climate modelers are doing as well. You know.
Any more questions?
Thought you were going to ask one, Tanya.
Oh, no.
Go back to VC then. Anyone from out there want to ask a question? Another question?
No.
No? Oh, well, so just probably quite struck Sheila about getting through a whole modelling talk without a single equation. And really
I knew Tanya was going to be.
Yeah.
and indeed that you actually admitted to getting your hands and feet wet. So Lily, just for me now to again thank you very much for giving your inaugural lecture, and indeed to everyone else for turning up in such numbers and supporting. So thank you, Sheila.
Thank you.
Ben to take over the next part of the proceeding.
Stand there.
Right, we're all going to look at Sheila while this is going on.
You're not going to embarrass me.
Of course. First thing, I'm going to ask you all to shut your eyes just for a moment. Forget the last hour and a half and think about what the popular perception of a professor is. What is the media's perspective? What is the person on the street's perspective of a professor? Right, you can open your eyes now. Right. I bet you some of you were thinking about Doc Brown in Back to the Future. Somebody like that. Bespectacled, socially awkward perhaps. I noticed that the front row, these professors were all asked to sit down on a piece of paper on a seat with something like this. So socially awkward perhaps, somewhat eccentric. And then think, thank God, we're in 2017, here we are, and here we have a new professor to welcome to our guild, completely opposite, no glasses, this doesn't apply. I don't know, you can decide about eccentric if you like. So in reality, what does professor mean? What does a professor bring with it? They only give a professorship to somebody that's highly accomplished, as we have just seen. a recognised expert by academics and regarded in their country and globally as at the top flight, the highest rank of academics. So what are professors? They usually have advanced degrees. We saw her chronometry work for her master's, we've heard about her PhD, and all the things she's done subsequently. They're acknowledged experts. We've seen some of the publications, we've seen some of the people she's worked with. There's no doubt she's a acknowledged expert. We see that they conduct advanced research. I think we can all agree that we've seen some advanced research right now, and that is published and put on Pure.
That's an in-joke for those of you.
Painful in-joke. And that they will supervise and mentor other staff and postgraduate students, and we've seen an excellent example of that just now. I did have the word nurture down in here. I'm not sure if nurture is quite the right word for Sheila. Cajole, bludgeon, perhaps. We've had to play God several times. But also they're ambassadors for the wider world, taking academia out there, as we've heard, taking difficult questions that politicians, policy might be grappling with, taking the data all the way through to answering those kinds of questions, being useful. And also, as a professor, it's an aspirational role, somebody that's a bit of a figurehead for people moving through their academic career to aspire to be something like that. And I think we'd all agree that Sheila's shown us a career that's worth aspiring towards. Usually, professors are at the top of their game in the university systems and academia. The professorships awarded to somebody that's the top of their game. And here we have Sheila that's reached the near pinnacle of our own institution. But just as she's reached this, she's got to the level to be with us all. She, like a butterfly, is about to take off and fly out into the wider world. And so we're delighted that she's going to move on from the University of the Highlands and Islands and SAMS. I should say, the director. Nick, our director, I've written it down. She's taking a leave of absence so she can come back. She's going off to Ostend to become the executive director of the European Marine Board. That's a fantastic position. And its strapline is advancing seas and ocean science. What better person and what better role can you be doing in that respect? Right, while her talk was going on, I was having a wee look at the dates that were coming up as she was going through her presentation. And I have now the dates of the University of the Highlands and Islands that has gone through. So back when she was formulating, I guess you were finishing your undergrad, you were formulating your ideas for your master's thesis on the Crum estuary. The idea of the University of the Highlands and Islands project was started moving forward in the early 1990s. At the point where you were writing up that your PhD, the Millennium Commission funding was awarded. As you moved around, you had been at SAMS when the University of the Highlands and Islands established, following the award from the university title of Privy Council and so on. So you've been here, you've been working for what we've seen throughout the whole time that our fantastic university's got to the position it is. So basically, we know that the university has been a big piece of work to get where it is, and Sheila has worked hard through all of that time to go to where she is. And so we're delighted on that point. I'm going to ask you to welcome her into the Professoriate. That's the group of 30 or more PhD professors that are in the University of the Highlands and Islands, our team working hard to bring things forward. And with that, I'm going to ask you to join me in applause for thanking Sheila for that, and I'll offer her a gift from the university.
Thank you.